Just a minute. Yeah, so please type in the chat box. Is the audio and video fine? Hi Ashwini, Kumar, good evening. So please type in the chat box. Is the audio and video fine? Good evening, all of you. Hi Artim. Yeah, so please confirm the audio and video once. If everything is fine, then we shall start this lecture. Yes, it's fine, right? Okay, so yeah, it's clear. Great. Then let us start. So of course, we are in continuation with this 7 p.m. batch of engineering mathematics, of course. And every day we are going to deal this class at 7 p.m. for 2 hours every day, 7 p.m. to 9 p.m. of course. And this is completely in English. Okay, so we have started this batch on Monday, and this is lecture number 3 of basically this engineering mathematics course. And we have started with the module linear algebra. Okay, and in today's lecture we will progress for the third lecture of linear algebra. We have covered 2 lectures in the past 2 days, on Monday and Tuesday. So this is basically the third lecture of linear algebra, and in this lecture we'll be majorly focusing on matrix algebra continuation and also determinants. Okay, sorry, will you teach DA maths also? Yeah, I have already told you I'll include it. Clear? Yesterday's one doubt is there. Yeah, if you have doubts, you're always free to ask. Okay, so if you have any doubt at any given point of time, you can always ask. Clear? So coming to this, if some of you are here for the first time, then definitely this is the Telegram channel which on which all the updates regarding this Wallah English channel will be posted. Okay, so if you want to get any updates or being notified of any sessions that are being conducted on this particular YouTube channel, you can just join this Telegram channel so that you will get notified. And if you have any personal doubts or anything related to the subject to talk about technical things, you can just or any personal guidance generally, you can join this Telegram group. This Telegram group is maintained by me and my students of PW. So you can actually scan this code and it will make you join into the group, of course. Okay, and you'll see basically this one feature we have recently updated in our YouTube, or basically to any students. So Unity, so I'll just quickly go through this. So if you just click Unity PW, then you'll have this first link. Okay, and this is how it shows. So once you click on login with Google, so you can just sign in with your Google basically Gmail details, and once you sign in, then you can have a page something like this. Okay, so you can see you will have a dashboard here, but of course since right now I did not participate in any polls, so it's showing 0 for me. But if you have started attending these classes, it would show record here. If you have any doubts, then you can actually start the doubt. Normally this is the chat box where you're typing your doubts. So here, before typing the doubt, you can type exclamation doubt and then start typing your doubt. Like let's say for example, if I ask you what is a determinant, okay, then you can click #doubt and then you can type what is a determinant. Then such doubts, what you type with the exclamation doubt in the beginning, they all get stored at one place in the Unity. So even in later stages, if you feel doubt during revision and all, you can just visit there. Similarly, if you want to make any note points, you can make exclamation note and then you can start typing your notes. If you want to type some notes, then exclamation note and then start type it. That also will get stored in this particular place. Okay, so here you'll have a track of all what you have asked or the complete year. Okay, not only till one day or one lecture or one subject. All your collection will be at this particular location. Okay, so please do register for this Unity app, Unity PW. Okay, and then moving forward to the last lecture. In the last lecture, typically we have looked at matrix algebra, right? So we were talking exclusively about symmetric and skew symmetric matrices and skew symmetric matrices in detail. We have talked about symmetric and skew symmetric matrices, and we have seen basically some important operations done with matrices. Okay, of course matrix multiplication is what we have seen, and we have seen certain important dealings with transpose of the matrix actually. Okay, so in today's class we'll extend this matrix algebra to some other few matrices, and then we will come to some important characteristic of a matrix which is called determinant. Okay, it's really very powerful. We'll see what is the power of determinant and what all it can do to a matrix. So we will look basically in today's lecture, we will focus basically on matrix algebra continuation to a bit maybe some first 30-35 minutes roughly, and then we'll skip into determinant and its properties slowly. Okay, so that's how we are going to deal in today's class. If things are clear so far, then I'm going to start today's lecture. So please confirm in the chat box, is everything fine? How it became commutative? Hi Krishna Najmohan. So how the orthogonal matrix is commutative and provide identity matrix. See, I have never told orthogonal matrix is commutative, because first of all you cannot say one matrix is commutative or not. Okay, some addition or multiplication, if you keep some operation, physical operation, then you can say it's commutative or not. Not for a single matrix you can say the matrix is commutative, but you can just multiply and tie out. If you just I have given you A transpose is equal to A inverse, that's what we have shown ultimately at the end. So if you take any orthogonal matrix and if you multiply the matrix with its own transpose, you will find an identity matrix. Okay, physically the operation tells you A is basically won't change the length, it only performs some rotation of a vector. Okay, so if you are doing the rotation, then ultimately the transpose is nothing but the inverse operation. Okay, like if you see in orthogonal matrix, if you see orthogonal matrix, we have seen basically if you have this A rotates a vector x by theta. Okay, in theta in a particular sense, in a anti-clock sense, let's say, for example, in a anti-clock sense, provided this matrix A is basically cos minus sine theta and cos theta. Okay, so this is the matrix that you have. Now let's say if you, for example, in few books you might have seen the minus sign here but not here, that tells you the rotation is in the clockwise direction. That's it. Okay, so it doesn't matter if I put a minus here or here, basically this matrix A turns the vector in theta in anti-clock sense. If I put this minus here, that means it rotates it by anti-clockwise. Okay, so we have seen basically A transpose is like performing rotation by theta in clockwise sense, of course. Okay, so if this is in clockwise sense, then ultimately you can see if you apply this A and A transpose together on a vector, then ultimately the vector remains there itself. Okay, they act like inverse of each other. That's it. A is inverse of A transpose and A transpose is also inverse of A. That's what we have seen in the last. Clear? And Haisa, can you say which topics you taught in this series will be under GATE CSE? All the syllabus. Okay, basically linear algebra, probability and stat, and calculus. Okay, and of course optimization techniques also I'll teach for single variable, which is in DA syllabus. Okay, orthogonal matrix become compute and provide. I have answered. I mean some matrix and transpose one. So I've done all the things, right? So no more doubts now. So tomorrow I had too much pain on eyes, so that I was not possible for in front of laptop too. But today morning I saw lecture. Okay, clear. Anyway, it is okay for XC aspirants. Yeah, I'm going to cover XC syllabus also. Clear? We'll talk about diagonalizations, algebraic multiplicities, geometric multiplicities. We'll deal lot of stuff. Okay, no issues. So anyway, we are continuing basically. So in the last lecture, yeah, okay, so fine. So in the last lecture, what we are talking is about the orthogonal matrix, and we have seen the transformations of an orthogonal matrix. Okay, so now let us go for some other types, which is 9. Okay, because I think orthogonal is 8. So involutory matrix. So sometimes there comes necessity where if you perform a matrix twice, it again gives back. Okay, this is like one special case of orthogonal matrix, but it can do anything. Okay, so orthogonal matrix is one special case where the length of the vector do not change, but actually it basically it only rotates. Okay, it performs only rotation. But let's say there is some matrix where if you have this X, for example, okay, so let's say this is XY system. I'm explaining in 2D so that things look simple for you. X, Y. Then if this is the vector which is having the coordinates x, y, for example, okay, so let's say x comma y, okay, fine, let's say alpha comma beta are the coordinates, okay, of this vector, then what an orthogonal matrix does is it rotates this vector first by an angle theta, and then if you apply A transpose, it again brings back and restore this vector x bar. That's what you have seen. Okay, but orthogonal matrix is only one specialization, okay, where length do not change. But let's say if I have a matrix in general, okay, so this involutory is like the generalization of an orthogonal matrix. Like for example, if I apply A on X, let's say I got Y, okay, so I'll get some different vector, because like let's say if I multiply a matrix A, B, C, D to this alpha, beta, maybe I'll get some number which is gamma, delta, okay. So let's say this is the matrix I got. Now this matrix physically, if you plot it on this xy plane, you will get some vector, and this vector along with having a rotation, its length also can change. It can happen, right? Because generally when you multiply a matrix on this, then ultimately it can change its length and also rotation. Okay, so it has rotated by an angle theta. Now if you apply this transformation once again, okay, this is what you have initially. So let's say if I multiply once more a y bar, this a y bar will again come out as x. That means this a square of x will be just equal to x. So that means this a square will be equal to identity matrix, because this vector should remain as this vector only if this a square is actually identity matrix actually. Okay, so sometimes we come across such situations. Of course right now I'm not doing in the physical things, but I'm just explaining mathematically. There come some situations where if you transpose or if you apply any transformation on a vector twice, there could be cases where you need the same vector again. Okay, especially in some points like strength of materials and elastica kind of things. What happens is this vector, after you perform two transformations of the same matrix, the vector should again trace back its original situation. So in such cases we will be in need of these matrices, and such matrices are called involutory matrices, of course. Okay, so basically the main definition is a square is equal to I, but the story behind a square equal to I is actually this. Okay, so anyway, this is just for understanding. I would like to write here a matrix capital A is said to be involutory, if a square is equal to identity matrix. Okay, like if I want to just give you an example, for instance, I could say example let a is equal to 4 minus 1, let's say. So if it is 4 minus 1, then fine, so we'll take 15 and then minus 4. Yes, I think this could serve good. Okay, yeah, 15. So yes, okay, so 4 minus 1, 15 minus 4, you take this 2 by 2 matrix for example. Okay, so if you calculate a square for this matrix, consider a square. So this operator a square is nothing but a into a. So if you multiply this 4 minus 1, 15 minus 4, 4 minus 1, 15 minus 4, of course, then you will see 4 4s are 16 minus 15 1. 4 into minus 4 plus minus 1 into minus 4 is plus 4. So minus 4 plus 4, this is 0. 4 15s are 60 minus 4 15s are minus 60. So 60 plus minus 60, it is 0. Then 15 into minus 1 minus 15 plus minus 4 into minus 4 is plus 16. So this is 1. So you can see this has given you an identity matrix. Okay, so there exists few important, see, if I keep on talking the types of matrices, I can talk a very large number of types of matrices. Okay, but we are discussing only some things which are previously on which there are few gate questions, and also which are physically very useful to you. Clear? So this is the significance of an involutory matrix. If you apply it even number of times, then it again brings the vector back to its original configuration. That's what. Clear? Is the concept of involutory matrix clear to all of you? Can you understand what does an involutory matrix do to any vector? Okay, Sridhar, Sneaky Snooper, nice names. So if two matrix multiplied gives identity, then its commute will also provide identity. Need not be. Okay, I got your question. Basically, if two different matrices provide multiplication of two different matrices provide identity matrix, this happens only if one is inverse of the other, and definitely they commute under multiplication. Okay, a into a inverse is equal to a inverse into a, which I'll show you after some time. So please do more sums in class. Yeah, I'll do. Okay, so today I have around some 6 to 7 questions which could definitely help you. Okay, so is this clear? The concept of involutory matrix, is this clear to all of you? If you perform it even number of times, okay, then definitely the vector restores in its original configuration. Clear? Every one of you. Yeah. Now let's get into one more interesting thing, which is 10 idempotent matrix. Idempotent matrix. Okay, so what is this idempotent matrix? Let's check it out. A matrix capital A is said to be an idempotent matrix if the matrix is effective, only once. only once. So what's the meaning of this statement? It's effective only once. That means, see, for example, if you have a matrix A and ultimately, okay, let me write it slightly here on this side. So if you have a matrix A and if you operate it, you'll get Y, of course, correct? So let's say if you take a vector X and ultimately if this A is operated on X, it will give you Y. 2. If you apply it once again, this will not change. Okay, means it doesn't matter how many times you keep applying A on this X, it can show its effect only for one time. Okay, so which means A square, A cube, all these things are again A, of course. Okay, so this implies A square X is equal to A times of X, because Y can be replaced with AX initially. So this can be written as A square is equal to A. And in fact, if A square is equal to A, you can say A cube is also A. Okay, why you can say that? Look, because if you have A cube, this can be written as A square into A, and since this is idempotent, I can replace this A square with A into A again gives me A square, so A square is again A. So A cube, A power 4, you can take any higher power as many times as you apply, it doesn't matter. This always can show the effect only for one time. Okay, so that type of matrices are called idempotent matrices. And I'll just give you an example. Maybe A is equal to 4 minus 1, let's take the same digits. So if you take that, then this is so let's say 3 times you are multiplying, so 12 and minus 3. Okay, so this is what you can do. In fact, you can take any two numbers and do the scalar multiplication of this, and you can write it here. So if you, for example, take this A square, let's see, 4 minus 1, 12 minus 3, 4 minus 1, 12 minus 3. So if you take this, then you will have 16 minus 12, 4 minus 4 plus 3 minus 1, 48 minus 36, 12 minus 12 plus 9 minus 3. This is what you have. Okay, and this matrix is again equal to the same matrix. Clear? So that's why if you have a matrix, it doesn't matter how many times you operate it on a vector, it can show its effect only for one time. Okay, so like you can see, A square equal to A, then ultimately A cube can also be written as A power 4 can also be written as A again. Okay, so all these things, they come up. Clear to all of you? Okay, so in fact, A square is equal to A, and this implies A cube, A power 4, A power 5, and so on. Whatever you do, this is all equal to A again. Okay, so please update DPPs to practice. Okay, we'll basically in the Telegram channel of Get Wallah English, we are going to plan some practice questions, which you will see from today itself, I think. Yeah, after the class. Okay, because I've already given 3 questions, they'll get posted. Clear to all of you? Did you understand what it is? Yes or no? Please type in the chat box. Everyone? 𝐂𝐤𝐬𝐿, Sagnika, Sridhar, Shashwata, Bhattacharya, Harikrishnan, Vasishta, Sneaky Snooper, Prabhahan, Manohan, yeah, all of you. Yes? So did you understand what's going on here? Identity matrix is both involute and idempotent. Yes, too. Okay? Now, let's go for one more type. 11. Involutory matrix. Sorry, involute I have already taught you. Fine. So we'll go for nilpotent matrix. Nilpotent matrix. Okay. So what is this nilpotent matrix actually? Okay. So let's see. A non-zero matrix A is said to be a nilpotent matrix, if there exists a integer n, or if there exists a scalar n, or a integer, basically can write, if there exists an integer n such that this n belongs to z plus, this tells you that n is positive integer. Okay, so this tells you n is positive integer, and a power n would be 0. A power n would be a null matrix. Okay, so few times what happens, like I was telling you in yesterday's class, there occur some terms where, like normally if you go for some advanced computations, you can find terms like a into some vector x, y, there is some non-linearity maybe in the equation, minus some x plus y, something like this is equal to 0, of course. Okay, so let's say there is some non-linearity in the equation. So clearly this is product of two things, so it is non-linear. So to eliminate these things, what we'll do, we'll multiply it once again. So if you multiply it with a once again, let's say if a square is equal to 0, a is not equal to 0 initially, but let's say a square is equal to 0, of course. Okay, then what we can do is this term, this non-linearity in the equation gets eliminated, because this a square gives you null matrix. Null matrix multiplied with x and y will eliminate the complexity of the non-linearity in the system. Got it? So that's how these equations are actually, this type of matrices are actually helpful to you. So anyway, I just give you an example, and here I can tell you one thing. The least value of n, the least value of n for which a power n is equal to 0 is called index of the nilpotent matrix. This word is important. Sometimes they can ask you in GATE or somewhere in few other exams. Index of the nilpotent matrix. Index of the nilpotent matrix. Like I can again give you one example maybe. So example, you take a is equal to say 2 minus 1, then maybe 4 minus 2. Okay, yeah, correct, 4 minus 2. Now clearly this is a non-zero matrix, but you can understand something. If I calculate a square, this gives you 2 minus 1, 4 minus 2, 2 minus 1, 4 minus 2, of course. So if you simplify this, 2 2s are 4, 4 into 4 plus minus 1 into 4, so 4 minus 4, 0. 2 into minus 1, minus 2, plus minus 1 into minus 2 is plus 2, so minus 2 plus 2, this is also 0. 4 into 2, 8, 8 minus 8, 0. Minus 4 plus 4, again this is 0. So clearly this term is a null matrix, of course. Okay, so there come situations where the power of the matrix itself for a non-zero matrix can turn out to be a zero matrix. Okay, and this also gives you one important conclusion. Product of two non-zero matrices can be a zero matrix, which I have already told you in the last class. Yes? Yes or no? Did I tell you product of two non-zero matrices can still be a zero matrix? We have shown in last class. Here it's one more example. You can see these two are non-zero matrices, but the product of these two turn out to be a zero matrix. Clear? Okay, so this is a square. And why I have mentioned this index of the matrix? This index word is very important. The reason is, let's say I have found this a square is equal to 0. Okay, if a square is a null matrix, ultimately from a square, a cube, a power 4, all these will be null matrices. Correct? Like for example, if I take a cube and if I ask you what is the value of a cube, you can add this a square into a, and since this is a null matrix, ultimately the product is going to be a null matrix. Okay, similarly it's only for the square, yeah, ultimately. Okay, because the higher power of the matrix, you are considering higher powers. Okay, see, I'll just tell you one thing why it is square. If this is a matrix m by n, okay, and if I am telling if you want to square this, then you have to multiply with m by n, and ultimately you can multiply these two matrices only if this n and m are equal, which means if these two are equal, then this matrix turns out to be a square matrix by default. Okay, Rahman, clear why we are doing it only for square matrices? If I want to raise the power of a same matrix, then ultimately this is what you have. Okay, this n should be equal to this m, which means ultimately this m and n should be equal, so that means this matrix should be a square matrix. Clear? Yes or no? Please type in the chat box. Fine? Yeah. So, am I audible, right? Because nobody start typing in the chat box. Is the things getting cleared or not? If you are facing any issue, please let me know. Please type in the chat box. Is everything on track? Are you understanding each and everything? Is it only for the a square? No, there could be few matrices where maybe the first 3 powers are not zeros, but fourth power of the matrix is 0. Okay, I'm telling there exists some integer value n where it starts getting the higher power of the matrix is equal to 0. Okay, that's what. Clear? In this case, it's like the second power index value is 2, but there could be matrices where index value could be 3, 4, 5, and so on. Got it? Okay, now let's see nilpotent matrix, of course. So I have got one question basically based on the last class. So let us solve this question. The minimum number of multiplications involved in computing the matrix product PQ are: matrix P has 4 rows and 2 columns, matrix Q has 2 rows and 4 columns, and matrix R has 4 rows and 1 column, is dash. I'm conducting a poll actually, integer type. I'm giving 120 seconds for you to check, or maybe, yeah, 120 is good enough. Solve this question. Yeah, that's also nilpotent. Okay, basically they should exist. See, if index is 2 fixed, then there is no definition of index, right? We need not specify again index especially, because for every matrix if the index is just 2, we need not specify it specially for all types of matrices. Clear? So index can be 3, 4, 5, anything. Come on, quick. 1, 0 cannot be, okay, because if a power 1 equal to 0, then a is 0 by default. Okay, then a is directly a null matrix, need not be nilpotent. Okay, okay, 48, 16, fine. Let's see. The minimum number of multiplications involved in computing the matrix product PQ are: matrix P has 4 rows and 2 columns, matrix Q has 2 rows and 4 columns, and matrix R has 4 rows and 1 column. Come on, do it. Gautami 16, Sagnika 16, Kids Gaming 48. Okay, let's wait for others answers. The poll is going up. Fast, come on, quick. Vasishta Arya 16. Okay, let's see. Fine, so let's see whether this matrix has got the answer 16 or not, because majority of you have told that. So let's look at it here. Matrix M or P, let's say PQR is what you are computing. So P is 4 by 2, Q is 2 by 4, and R is 4 by 1, of course. Okay, so if you want to calculate PQR, then ultimately you can do it in 2 ways. First you calculate PQ and then multiply R as post factor, or QR you calculate first and then multiply P as P factor. Okay, so first of all, to calculate PQ, how many multiplications do you need? Okay, so PQ is of P is of size 4 by 2 and Q is of size 2 by 4. So 4 2s are 8, 8 4s are 32. So you need 32 multiplications in order to calculate this PQ. Okay, so now what is the size of PQ? PQ would be ultimately of size 4 by 4. Okay, so this is of size 4 by 4 and R is of size 4 by 1. Okay, then number of multiplications you need here is 4 4s are 16, 16 into 1 is 16, of course. So this is 16. So clearly, first to calculate this PQ you need 32 multiplications, and then after to calculate this PQ into R you need 16 more multiplications. So total multiplications you need is 32 and plus 16. So sum of multiplications, or total number of multiplications you need in this manner, total number of multiplications you need is equal to 48. Okay, so total number of multiplications you need is 48. Now coming here, this is also one more possibility of calculating PQR. So if you calculate QR, so first of all, to calculate this is of size 2 by 4 and this is of size 4 by 1. So if you multiply these two first, 2 into 4 8, 8 into 1 is 8, of course. So you need 8 multiplications first of all to calculate QR, and size of QR is 2 by 1, of course. Okay, then again to multiply this P with QR, so P is of size 4 by 2 and QR is of size 2 by 1, of course. Okay, and to multiply these two again you need 4 into 2 8, 8 into 1 8 again. So again you need 8 multiplications. So total number of multiplications you need in this case, total number of multiplications you need is equal to how many? 8 first of all to calculate this QR, and then after one more 8 multiplications you need to multiply this, so total 16 multiplications. Okay, so in one particular way you are getting 48 multiplications, and in another particular way you are getting only 16 multiplications, and in the question they have asked you for the minimum number of multiplications, so ultimately this is 16. Okay, this is also a previous gate question, so I have just put it here. 16 multiplications is what is the minimum number of multiplications in order to multiply those 3 matrices. Okay, so let's check the poll. 16 view results. Okay, 80% of you have done it right. Sagnika, Gautami, Ashwini Kumar, Vasishta, Arya. Good. Okay, so I think even after 120 seconds some of you might have done, but it's good. Okay, yeah. So let's get into more things. Okay, so nilpotent is what we have seen, of course. Then we have understood certain good points about matrix multiplication. Okay, now one point I'd like to give you is, in last class which I did not give you intentionally. So matrix multiplication is distributive. Matrix multiplication is distributive. That's nothing but, if you have A multiplied with B plus C, this can be written as AB plus AC. Or in general, if you have this term, you can take A common and you can write B plus C, of course. Okay, this is always done. And for every, okay, for a non, okay, we'll talk about singularity once we teach determinants, fine. Okay, so this property holds, because if you want to multiply individually AB and if you want to multiply individually AC, then the obviously number of operations is large in this case. Okay, to eliminate that, we can come here. It's almost like doing only half of the operations than what you do here in case of multiplications. Okay, so that's the idea basically. Now we'll move on to the concept of determinants. Okay, so matrix algebra is clear to all of you. So why multiply with the 1 in RQ? Where in RQ? In the previous question? In the previous question, RQ. I did not get you. Why multiply with 1 in RQ? Where is capital I into Q? There's Q into R. Okay, maybe this talking. And Rahman, this QR and RQ need not be equal. Okay, so if this is in QR, you can write only QR. See, in yesterday's class, I have taught QR need not be equal to this RQ. Okay, so this is what you have. So basically I have told in the last class, if you want to multiply two matrices, let's say if you want to multiply these two, m by n and n by p, of course, then number of multiplications is m into n into p. That's what. Okay, in last class I have shown it, so please go for the video once again. Now let's see what is a determinant and its properties. Okay, so what is a determinant and basically why we actually calculate determinants. Okay, so what you want to know by calculating something into something and all. Okay, so some a11, a22, whatever you calculate, why you need that determinant and what makes you calculate the determinant actually. Okay, so let's see. I want to tell you one thing. In last class we have talked about diagonal matrices, correct? You all have studied diagonal matrices. Tell me one thing. Okay, so tell me one thing. If I give you one system, for example, say 2, 3, maybe -1, 2, x, y is equal to 3, 4. So let's say you have this system, for example. Then to solve this system, of course you will do some calculations and all. It's a 2 by 2 system, simple system I have given just to make the things understandable to you. In this 2 by 2 system you can solve, normally when you can solve, a lot of methods are there, elimination, substitution, a lot of things you can do. But let's say if you want to solve this using matrices. Okay, right now do you all have some basic idea about solving of matrix system of equations? Do you all know something called Gauss elimination? Have you ever studied Gauss elimination? Have you studied Gauss elimination? Have you studied Gauss elimination actually? No? Okay, fine. If no, it's fine, no issues. I'll tell you one thing. Forgot, sir, actually. Okay, cool, no issue. The biggest gift what God gave humans is forgetfulness, correct? Yes or no? No, it's okay. It's okay. If you don't know, it's fine. I'm not assuming that you know Gauss elimination. It's okay, cool. But one thing that really God gave a gift to the human beings is to forget something. Okay, obviously you don't remember few things as much you remember on the first day, right? Like let's say if in someone's family some tragic incident has happened. Okay, then obviously our pain gets reduced and eventually we keep forgetting things. Yes or no? We forget sad moments in our life. Okay, so correct? So actually forgetting is something good which you can do, but not in exams, okay? Anyway, let's see. I want to tell you one important thing. If you construct a matrix like this, 2, 3, minus 1, 2, and this is 3, 4, okay? So 2, 3, minus 1, 2, and you have 3, 4, of course. Then let's see if you try to make this matrix, okay? So by doing some few things, okay, we'll see what are those few things eventually when we go this course. So let's say you have converted this matrix into the form A, B, C, 0, D, E, okay? So you have done something, but you have converted this matrix into this, but only by performing our transformations, okay? So when you do this transformation, okay, so you have done something such that this matrix which is initially in this form got converted to this form, okay? Now if you write this back in form of equations, you have Ax plus By is equal to C, 0 plus Dy is equal to E. This is what you got, okay? This is what you get. Let's say somehow you have converted this matrix into this form. We'll see how to convert and all as we progress in this course, but let's say you have got converted this, okay? Then ultimately if you write this matrix equation back into the system of equations, then this is what you get. Now when you get this, you can easily identify this y value from this equation is nothing but E by D, of course, okay? So you get y equal to E by D, and similarly here you will get, if we put y equal to E by D, then this is a single equation with single unknown, you will get what is x also. So which means it is always suggestible to calculate this matrices or basically to convert this matrix into this form, and so that you can get the answer very comfortably. Yes or no? Did you understand what I'm telling you? If you, by using some technique, doesn't matter what it is, if you can convert this matrix into this form, it's always easy for you to solve your solution of the system. Yes or no? Correct? Will you agree? These elements will also change, but let's say you have some numbers here, okay? So C, E, A, B, D, all these are numbers. Then ultimately it's very much easy for you to solve the systems. Okay, of course I have taken an example of 2 by 2, but you can go for any 3 by 3 or 4 by 4, whatever. Now the main crux here is, if you have a system generally Ax is equal to B, for example, okay? Ax is equal to B, and let's say I want to calculate what is the unknown vector, okay? Means let's say this is my x bar, my unknown vector, and if I want to calculate this unknown vector, for example, then let's say if I multiply a matrix C on both sides such that if this can give me some diagonal matrix or identity matrix. So let's say here, because of some reason, let's say this element has also got to 0, then this calculation is much more easy. Yes or no? Previously you have to do something, but now you need not even do that. Directly you can say x is equal to C by A and y is equal to E by D just by looking. Means converting this matrix which is in the coefficient into some diagonal form can actually reduce your effort to a great extent. Yes or no? If this matrix can somehow be converted to this diagonal form, then ultimately the solving becomes very much faster and easy in solving the systems. Can you understand this or not? Can you understand this or not? Can you understand this or not? If this matrix is somehow converted to this form, then ultimately solving this vector is very easy for you. Correct? We'll see examples, we'll see just a minute. Now one matrix that always converts this product into identity is C, is basically called adjoint of A, okay? This matrix, when you multiply to this matrix A, always this product gets converted to this form, and in fact this will also be A actually. That's what, okay? And rather than calculating this solution, just multiplying two matrices is very easy, and here you have identity matrix. So I into and some scalar, maybe some scalar k into I is equal to this product of two matrices, which can be easily calculated. So then if you just divide this k on both sides, then you have I into x is nothing but x. So x is equal to product of two matrices divided by some constant, and matrix multiplication is very easy, which anyone can do, and you can get what is this x actually. And in this whole story what I have taught, this k, whatever you're getting, is called determinant. Okay, so we will see what is this determinant and what are cofactors, how this matrix adjoint of A. This adjoint is always lying side beside of this A, and this adjoint, when you multiply to this A, will drastically simplify this system to a diagonal matrix, which you can actually to a scalar matrix actually, where all the principal diagonal elements are equal, and then you can easily solve this system. Okay, so we will see how to do this and what is determinant and all in this case. Okay, but this is just an outline what I'm giving to introduce determinants. We'll do much more formal introduction. It's not Gauss-Jordan actually. Okay, we'll see. Okay, so it is a matrix transformations. We'll see what happens. So determinant. This definition was asked once in DRDO interview also. Okay, so they told what is determinant of a matrix, and people started telling AD minus BC, all these answers. Okay, so AD minus BC is the determinant of only one particular matrix, which is of this form, AD minus BC. If I change these two positions, A, B, D and C, then the determinant of this matrix is not AD minus BC, you know, it is something different. Okay, so we will see what is determinant and what all things we have. Now, determinant is nothing but the sum of product of elements of a row or column of a matrix with their corresponding cofactors. With their corresponding, this word is very important, with their corresponding, and I'm introducing one more word, cofactors. Cofactors. Okay, so cofactors. So what is this cofactor and why we actually do this product of sum of product of multiplications and all, we'll see. We'll go sequentially. Look, I am taking an example of 3 by 3 case so that you can understand things better. Actually, I would have gone to much basics than this, but the things will get complicated, and that is not anyhow required within the gate level of understanding. So see here, minor of an element. Minor of an element. So what is this minor of an element actually? The minor of an element is defined in a particular way, because geometrically it's much more complicated to explain in a generalized sense, but just I'm explaining with the help of a 3 by 3. If you take a minor of an element Mij, okay, so let's say minor of an element Aij, for example, you take any element Aij, then let's call this as Mij. Okay, so this is called minor. So how do we calculate minors? Okay, I'm not defining what is a minor again, because geometrically going to it is complicated. So just I'm explaining you how to calculate minor, that's it. Okay, we're not physically going into what is a minor in this case. Now let's see, if you have this matrix A, for example, A11, A12, A13, I'm taking 3 by 3 so that you can understand things better. It takes time to explain, but still you will be happy. For a 3 by 3 matrix, the minor is defined in this form. If you take, for example, this element, okay, so let's say I equal to 1 and j equal to 2 is what I have fixed. If I take I equal to 1 and j equal to 2, the minor of this element is nothing but minor of A12, which is nothing but capital M12, is A21, A33 minus A31, A31, A23. This is what you have. Okay, so product of these two elements minus the product of these two elements again here. Okay, so product of these two minus the product of A31 and A23. Now let's see, this is how we have defined the minor in this case, and the minor is basically, we'll see, it's like a nonlinear equation again, looping in. So basically the minor is nothing but, if you delete this row, for example, okay, so let's say if I delete this row and if I delete this column, then whatever the matrix I have, the submatrix, okay, so yesterday someone is asking what is a submatrix. In a given matrix, if you delete some rows or some columns, then the matrix which you have in the resultant form is the submatrix actually. Okay, so submatrix is obtained by why that elements, we'll see. Okay, we'll see by the time of ending you will come to know why we have taken only this particular combination. So see here, if you take this element, if you delete this row and this column, then this matrix whatever you have A21, A23, A31, A33 is called submatrix. Okay, so submatrix is obtained by deleting some rows or some columns of a given actual matrix. Okay, now let's see similarly if you want to calculate, if you take this element, okay, for example, or A23 you take. Okay, so if you take A23, now if you delete this column and this row which is basically containing A23, then it is defined of the form M23 is equal to M23 is equal to, so if you delete this, then this is the higher side, so A11 A32 minus A11 A32 minus A12 A31 A12 A31. This is how the minor is defined. It's basically the it is basically the product of cross elements minus the product of this particular diagonal, okay, of the submatrix. That's what we have taken. Okay, now similarly you can generate total 9 minors for this 3 by 3 matrix. Okay, so it's a 3 by 3, so clearly you can generate 9 minors because minor of A11 A12 and so on till A33. Now we define this word which is called cofactor of an element. Cofactor of an element cofactor of an element which is normally called capital Aij. It is denoted with capital Aij. Okay, so small aij is for denoting the elements of the matrix. This capital Aij is the denotation for the cofactor of small aij. Okay, now let's see, this Aij is defined as -1 whole power I plus j times Mij, of course. Okay, so this is how it is defined, means to the minor whatever you get, this -1 whole power I plus j. Okay, so again I'm telling, I'm just giving you how to calculate this minus and cofactors. I'm not explaining the physical significance because if you go in deep into the vectors, the stuff gets more complicated. Okay, so we are cutting it all down at this point. So this -1 whole power I plus j times this Mij, capital Mij, of course. Okay, now if you try to understand one thing, ultimately A is equal to A11 A12 A13 A21 A22 A23 A31 A32 and A33 is what you have. Okay, now if you look at the cofactor matrix, for example, cofactor matrix is the matrix which contains cofactors of all the elements in the same sequence. So if I am calling capital Aij as the cofactor of element Aij, then ultimately I have the matrix A11 A12 A13 A21 A22 A23 A31 A32 and A33. This is what I'll get, correct? So here, like for example, you see how I have calculated A12. So if I want to calculate A12, -1 whole power 1 plus 2 into this term, means this product into -1 whole power 1 plus 2, this total term what I am getting, that's nothing but my A12. Is this clear to all of you how I have formed this matrix? Yes or no? Basically for each element in this matrix I am calculating a cofactor and I am again putting them together in a matrix form, because of which I am getting this cofactor matrix. Okay, is this clear? Yes or no? Please type in the chat box. Is that clear to all of you? Okay, so type in the chat box, each and everyone. Is that clear? Did you all understand how did I form that matrix? Now let's see if I transpose this matrix. Okay, so if I transpose this matrix, why I am transposing, this information is enough to define what is determinant, but still to make the job easy I am transposing this matrix, and we define one more word which is adjoint matrix. So it is normally denoted with adjoint of A, of course. Okay, so adjoint of A. Now let's see, adjoint of A is nothing but cofactor matrix cofactor matrix transpose. Okay, so we have cofactor matrix transpose. Why I am transposing, you'll come to know in just 1 minute. So this adjoint of here is nothing but just transpose of this matrix. We won't achieve much anything bigger advantage by doing transpose, just for the easiness in the calculation. Okay, now I want you to consider one thing. Consider A times adjoint A. Okay, so let's say you consider this. Let's say this is one matrix what you have obtained by doing certain calculations, and this is the initial matrix capital A. Now if you multiply these two matrices, let's see what happens. Okay, so this is an interesting story. Look, A into adjoint of A. Okay, so this tells you A11, A12, A13, A21, A22, A23, A31, A32 and A33, of course. Okay, so this is what we have multiplied with capital A11. Now this is actually the cofactor matrix. If I transpose this A12 will actually come here. So this matrix is written as A12, A13. Similarly A21, A22, A23, and you have A31, A32 and A33, of course. Now if you multiply these two matrices, let's see what happens. In the first column element, you will have A11 into capital A11 plus A12 into capital A12, A13 into capital A13. So this is nothing but the first element of this first column element of this product matrix is nothing but the product of elements with their corresponding cofactors, and of course you are adding them. Like for example, you are multiplying cofactor of A11 with this small a11. Of course this capital A11 is nothing but the cofactor of this small a11. So you are multiplying the element with its corresponding cofactor. Similarly you are multiplying element A12 with its corresponding cofactor. Similarly A13 and capital A13. Now you are summing up these products. Now as per the definition of a determinant, what I have defined, the sum of product of elements with their corresponding cofactors is called determinant. That means the first column element, whatever you are going to get here, is nothing but A11, capital A11, A12, capital A12, A13, capital A13. So this form is nothing but for any row or any column is what I have told. So this value is equal to determinant of A actually. Clear? Is this understandable to all of you or not? I am telling you, since I have defined this determinant like this, you can see the sum of product of elements of a row or column of a matrix with their corresponding cofactors, and here this column is nothing but the cofactor column for this particular row, and if you are multiplying this by definition of determinant, this summation whatever you have done here, that would be equal to determinant of A, of course. Clear? Yes or no? Yes? Can you understand this? We are actually summing up the terms which contain product of an element with its corresponding cofactor. That's what I have written. So this value is nothing but determinant of A actually. Clear? Now let's see one more point. Okay, so let's see one more thing. If you calculate the first or second column element, multiply this with cofactors of the second row actually, okay, because these are the elements, but this column is actually not the cofactors of the first row, it is actually cofactors of the second row. Okay, so let's see what happens. A11, A21 plus A12, A22 plus A13, A23. This is what we have. Similarly the last element would be A11, A13, sorry, T1 plus A12, A32 plus A13, A33. This is what we get. Similarly, I am just writing the other elements. Now, if you do with the second row, we have A21, A11, A22, A12, A23, A13. Okay. Now, let's see A21, A21, A22, A22, A23, and capital A23, of course. Okay. Then coming here, the last step again, A11, sorry, A21, A31, A22, yeah, correct, A22, A32 plus A23, A33. You need not write this, just for your understanding I'm writing. Okay, you can just write the final answer what I'm going to write, but this is just for your understanding. Okay, next, similarly if you do with the third row, you have A31 A11 plus A32 A22, sorry, A12 plus A33 A13. Similarly here A31 A21 A32 A22 A33 A23. Okay, similarly in the last, let's see what happens. A31 capital A31 A32 capital A32 plus A33 capital A33. This is the matrix that you're going to get, of course, but also explain with a complete question. Yeah, of course, we'll explain. Okay, so just right now what I'm doing is just doing a matrix multiplication, that's it. Okay, now you can understand, if you see intentionally I have drawn these diagonal elements with blue ink. The reason for that is this element is nothing but the determinant of A. Similarly, if you come here, if you take the second row, for example, if you take this second row, the elements in this second column are nothing but the cofactors of these elements, correct? So whenever you dot this vector with this vector, ultimately you will again get one more determinant, correct? So A21 into capital A21, because this is the cofactor of this A21. Similarly, cofactor of small a22, cofactor of small a23. So this will again give you the definition of determinant. Likewise, this is also give you the definition of determinant. But if you look at the yellow elements, okay, this clearly the blue elements has given you determinant, 100% sure. Now what about these yellow elements? Okay, so let's check it out. I'll show you for one element. Okay, you can do the same thing for others. Let's say if I consider A11 A21 plus A12 A22 plus A13 A23. Okay, so let's say I have done this for example. Now let's see, this value is equal to A11 into what is capital A21? Let's see, capital A21 is nothing but the cofactor of the element, so minus 1 whole power 2 plus 1, which is 3 into M21, okay, plus A12 into minus 1 whole power 2 plus 2 into M22 plus A13 into minus 1 whole power 2 plus 3 into M23. This is what you get. Okay, now if this is what you get, then let's see, this is minus 1 whole cube, so this is minus A11 into M21. So what is M21? So let's see, this is the second or first column element. So if you delete this row and this column, you have A12 A33 minus A32 A13. Okay, so A12 A33 minus, okay, so A12, if you delete this row and this column, you have A12 A33 minus A32 A13. This is what you have. Okay, so this is what you get. Then minus 1 whole power 2 plus 2, this is power 4, so this is plus sign, this plus remains as it is. So A12 into M22. So M22, let's see, if you want this minor of element A22, then delete this column and this row, you have A11 A33 minus A13 A31. Okay, then after plus, then this is again negative sign, so minus A13 times of M23. So what is M23? We have calculated already. A11 A32 A11 A32 minus A12 A31. So this is the total expansion of this first this element. Okay, so this second element. Now if you simplify this, let's see what you'll get. Clearly see, you have minus of negative A11 A12 A33. Here you have plus A11 A12 A33. So can I say this term when you multiply with A12 and this term when you multiply with minus A11, they get cancelled, yes or no? Similarly, you have this minus into minus plus A11 A32 A13 A11 A32 A13, but this is a plus because minus of minus, but here it is only minus sign and here it is plus. So this term when you multiply with minus A13 and this term when you multiply with minus A11, they get cancelled. Similarly, this term and this term will get cancelled and finally you will get only 0. Okay, so that tells you if you multiply any elements of a column of a matrix with other cofactors, okay, not corresponding cofactors, with other elements cofactors, with cofactors of other row or other column, you will definitely end up with 0. You can do it for any row if you want. Like you can check any of the yellow elements, you will definitely get 0 actually here. Got it? Yes or no? Are you all understanding this or not? Please type in the chat box. Yes or no? Please type in the chat box. Is this clear to all of you or not? Did you understand? This is 0. In fact, you take any yellow colored element, you will end up with 0 actually. That's what I want to say. Now, do you know why your determinant is actually calculated in this form? Look, I'll just tell you. Before I go forward, A, B, C, D, E, F, G, H, I, for example. Okay. So let's say if you have this determinant, you know, if I ask you to calculate this determinant, I think many of you are familiar. A into EI minus HF minus B into DI minus FG plus C into DH minus EG. This is what you guys gonna do. Yes or no? You will calculate this and tell me this is determinant. Now many of you might have a question, why this plus and minus is going alternation? Okay, so plus minus again plus. Why these plus minus alternations are coming? The reason is when you are multiplying cofactors, to calculate this A11 you have minus 1 whole power 1 plus 1. To calculate this A12 you have minus 1 whole power 1 plus 3. To calculate this you have minus 1 whole power 1 plus 3. Okay, this term is plus 1 and this term is also plus 1, but this term will actually give you, this is 1 plus 2 actually, sorry, this is 1 plus 2, the total answer is 3. So this term will actually give you 1, but this term will actually give you minus 1, and that's why, since this is the element with respect to first row is what you are calculating the determinant. So with respect to first row, if you are calculating the determinant like how I have done here, then this minus sign comes up from this minus 1 whole power 1 plus 2 actually. Okay, so in fact you can write this as plus sign in all the 3 terms, but eventually we are habituated to put this minus because of this minus 1 whole power 1 plus 2 actually here. Got it? Okay, because if you are calculating this, you are expanding about the first row. Okay, I would have expanded about the second row also. Okay, the answers might the answers won't change actually. Okay, now let's see. So clearly one thing is very sure, these elements, they turn up to be zeros. You can check if you want. You can, I have shown you for one element. In fact, you can go and check for any other element. Okay, now the advantage here is you have, therefore A into adjoint A gives you one very beautiful matrix, which is, you can see, determinant of A 0 0. Then in the second column, in the second row, 0 det A 0 0 0 det A, of course. This is the matrix that you have, and more importantly, this matrix is a scalar matrix, which means even all the principal diagonal elements are equal. Okay, so this implies A into adjoint A is equal to, of course, adjoint A into A. This is also same, because if you just try the reverse, the same thing will happen, because if you just flip these two matrices, these terms will flip, that's it. Okay, but you will have the same combination again. Okay, so therefore this matrix is always equal to det A times I, of course. Okay, so that's why this result, this definition of adjoint calculation is very important. Okay, so it gives you diagonal matrix. So whenever you have things, okay, so let's say if I have a system like AX is equal to B, for example. Okay, and let's say instead of calculating A inverse, okay, calculating A inverse is very troublesome, to be frank, because you have to calculate this adjoint and then divide all this stuff. So if you somehow have this adjoint matrix, okay, without calculations, if you somehow get this adjoint matrix, if you get this, if you multiply this adjoint on both sides, what it does is this term will give you an identity matrix with some scalar multiplication, which is that det A actually. Okay, now let's understand something. A into adjoint A is equal to det A into I, of course. So this tells you A into adjoint of A is equal to det A times I, of course. Now if you multiply with A inverse on both sides, okay, because if you want to calculate A inverse into A into adjoint A, if you multiply with A inverse on both sides, det A into I, okay, A inverse, det A is just a constant, you can bring it out. So det A times A inverse into I is what you'll get. Now A inverse into I is just again A inverse, so you will see this is A inverse again because into identity matrix, and this gives you identity matrix, of course A inverse into A is I, so I into any matrix gives itself, so adjoint of A is equal to det A times A inverse, which means you can say A inverse is actually 1 by determinant of A into adjoint A actually here, correct? So you can see this is what you have finally for the calculation of A inverse. Okay, is this fine to all of you? And that's why if this matrix has to exist, this is, since this is in the denominator, this denominator should not be equal to 0 because division with 0 is not defined. So this matrix should not have a 0 determinant if this inverse has to exist. Clear to all of you? Yes or no? Please type in the chat box. Is the understanding clear? Each and every point what we have done. It's just 3 slides. It took me 1, 2 maybe. Okay, this is just multiplication and some bit of understanding. Okay, so choosing the minor in a particular combination tells you that this multiplication will yield a diagonal matrix with equal elements actually. Fine. I think people are busy in writing notes. Please type in the chat box here. Just a minute. I'll have some water and come back. Is everything understandable to you or not? Please type in the chat box. Each and everyone who is online, please type in the chat box. 1 hour completed, sir. So you're expecting some story from me. Okay, I'll tell you. Okay, so look, fine. So 1 hour completed. So you want me to tell some story now? Good. Sorry, you're following time. In fact, it's 8. Yeah, of course. Okay, what story should I tell you today? Good. So let's see if I ask you something like, let's say for example, okay, so okay, I'll explain one nice thing for you. Some motivation maybe I'll give you today. After telling the complete story, you tell me whether it is motivation or demotivation. Fine. Okay. So let's say, you know, people write this statement. Hard work is the stepping stones to success, whatever, you know, failures are the stepping stones and hard work is, you know, key. They tell a lot of things. Okay, so let us try to prove this mathematically today. Okay, hard work is key to success, of course, and people say hard work always pays off, a lot of stuff they say. So I'll tell you one thing. Let's say I take 3 persons. Okay, you have A, B and C. You have 3 persons. Okay, is it like we just define inverse of a matrix? If we multiply the matrix with its normal matrix, we'll get identity. It's not normal matrix, it's basically adjoint, which we got. So class notes are available in PDF format. Yes, Dhanush, basically in the free batch that you have the link, okay, in the description, you can go there, you can get the notes of that. Okay, so see here. So now let us take January 1, or let's say maybe today's date, April 17, 2024. Okay, so let's take, you take the day April 17, 2024, and let's say these 3 persons are basically on the same skill set, same set of knowledge and same intellectual levels. Each and everything is same. So let's say I am taking the value of all these people to be 1 actually. Okay, so means if you want to give ratings to them, then this is 1 on each case. Okay, because all of 3 are equal. But now this guy is hardworking, and this guy is just going with the things, and this is a bit lazy. Okay, so as of today, let's say the value of all these three people is same. Okay, now let's say this hardworking guy, what he do? Daily he push up his limits. Okay, so he keeps pushing his limits, and daily he'll try to acquire knowledge. Okay, so by some source he always every day put some effort and will try to generate some knowledge, so that every day he's getting improved by just 1%. Okay, 0.01. Clear? So this person is every day gaining a knowledge of 0.01, adding. Okay, so it's slightly increasing his knowledge, 0.01. And this guy, as he is just going, he keeps him at the same place every day. Okay, he don't want to learn anything. At the same time, whatever knowledge he has, he just want to continue with that knowledge. Okay, this guy is a bit lazy guy. So this fellow, instead of learning, he is not even working, he is going to the negative side, but of course very small amount, 0.99. Okay, so he is doing a hard work of a small amount every day. So 1.01 is what his value is increasing every day, and this value is slightly decreasing every day. Okay, because slightly, very slightly, 0.99. And this happened for 1 year, let's say. Okay, so this job happened for 1 year, so that in 1 year every day this person has tried to increase his level. So he's doing some pushing his limits a bit and trying to get increase a 0.01. This fellow is just where he is, and this fellow is slightly lazy, he is slightly decreasing. Okay, now after 365 days, what's happening? 365 days is very fast, correct? You might have written GATE 2023, 2024, and you might have observed 1 year has turned very fast. So after 1 year, exactly if you check them on April 17, 2025, for example, then this person, since he has done a hard work of 0.01 every day, this goes up for all 365 days. Then this person, he is staying where he is, so 1, he is 1 on all the 365 days, and this fellow is daily keeping decreasing his levels. You can see 0.99 power 365. Now exactly after 1 year from today, the values, if you check, I have got a calculator. Okay, so we'll have a calculator today. So see here, 1.01 power 365. Okay, so 1.01, I hope you all can see the screen. 1.01 power 365, this gives him 37.78. 37.78 is the value of this person within 1 year. Because of this progress, he has got to a value which is roughly like 37.78. Now coming to this guy, he is at the same place where he is previous year, this year, wherever he is maintaining the same. He don't want to improve. Now coming to this guy, 0.99 power 365. Can I click the equal to sign? You know what happens? 0.0255. His value has got decreased by 100 times, actually, almost. Okay, because it is 0.02, so 98% of his things are already gone. Clear? You see the difference. Okay, that's why the small efforts, they do count. This 0.01 can make the increase of this person from 1 to this within a span. Clear? So that's why, of course, it's just a bit of mathematical calculation I just want to show you, but mainly the thing that I believe is, and not only believe, I have seen enough results among my students for past 6-7 years, is people who work hard, they ultimately get succeeded. Maybe they get delayed in success for 1 year or 1.5 year, things happen, but definitely they'll see the success. Okay, normally if you see check people, hard work and basically efforts. Okay, people who are smart and people who put efforts, they're unstoppable and unbeatable, of course. But people who are not smart but they are working hard and trying to achieve things, definitely someday they are going to achieve. And people who are just smart but not hardworking, it depends. Okay, their smartness may work or may not work sometimes. That's it. Okay, fine. Shall I tell you one thing, guys? People tell you work smart, don't work hard, all this stuff. Okay, but first of all, to work smart, your mind must be smarter, and if your mind want to become smart, then definitely you have to work hard in the beginning, in the initial stages at least. Okay, so you will have using the calculators. So is it important to solve PYQs? If yes, can you please suggest some sources? Thank you. Like how to solve PYQs and all, I have done one video on this channel. It's on the it's uploaded actually. You can go to that video. But anyway, in the short sense, I'll tell you, because there's a question: is PYQs important? PYQs are very, very important. It's not like they are just important. They are very important. In fact, in the first class also, I've been telling you, 60% of the paper, like almost 60 marks in and around, if you can solve all the PYQs thoroughly, and if you go for the exam, definitely you can get somewhere above 65 marks easily. Okay. The reason is if you look at PYQs, okay, of at least some, say for example, starting from 2013 or 2014 to till now 2024, you'll see many times you will find yourself that the questions are getting repeated. Okay, may not be the same questions, but the knowledge that you got by solving previous year questions will be definitely able to is good enough to solve the present questions actually. Okay, so that's why PYQs are very important in solving GATE exam, not only in GATE, in any exam in general. And of course, we had launched a book last year also. We had the solutions and video recordings in that book. I myself and one more faculty from civil branch has recorded the math solutions actually. So if possible, try to get a copy of that and start solving questions. Okay, because when I teach in the class, it's not possible for me to cover all the PYQs. I'm putting only those things which are slightly tough for you, but it's always good for you to practice things. Okay, and which branch student should solve what PYQs? I have done a video on this channel just a few days back before starting this course, so please have a look at that video. It could be very good. Okay, fine. Okay, things clear to all of you? What are the most mandatory sources of practicing questions for GATE exam? PYQs. Okay, PYQs. See, first you ask any of your senior who have written GATE examination but did not do well, unfortunately. You go to such seniors and ask, have you solved all your PYQs? Definitely they'll say no. Okay, the reason, once you don't solve PYQs, you don't have enough understanding on what kind of questions are coming on exams. Okay, test series is something which is at the later stage, but before going for the test series, first you should have thorough idea on PYQs, and then only you can go for test series or whatever platforms and all that exist. Okay, PYQs are the most important things. Clear? And you can get PYQs even from the GATE website. Okay, or basically in GATE website they are unsolved, but in this PYQ books and all, you can expect solutions. Okay, clear? So anyway, let's get back to the story. So we have calculated the inverse. Okay, so inverse, and this is basically determinant, and we have seen what is a determinant. Determinant is basically the cofactors. So determinant physically signifies to what maximum extent a matrix can change the length of a vector. Okay, so determinant, I'm just writing it here. Determinant physically signifies the maximum change or the greatest change. The greatest change that a matrix can do to a vector. To a vector actually. Okay, so to a vector. Now let's see properties of determinants. Okay, so you have seen basically how to calculate determinant and all, you know. See, I just want to tell you a few more things. To calculate determinant, there are a lot of techniques, tricks and all, but to be frank, within the GATE examination domain, okay, like I'll just tell you one thing. If I want to calculate this A11, A12, A13, A21, A22, A23, A31, A32 and A33, of course. Okay, so A33. Now let's see, you can write this determinant as A11 into A22, A33 minus A23, A32 minus A12 times of A21, A33 minus A31, A23 plus A13 times of A21, A32 minus A31, A22. Okay, so this is basically the determinant. Now if you want to calculate this, you can also, you have plenty of ways to do this. One of the ways which I can do is, you take the same determinant A11, A12, A13, A21, A22, A23, A31, A32, 3 of course. Okay, then let's see what I can do is I can write this element here. Similarly, this element here, I can write this a11 here and this a31 here. Okay, now let's say I'm multiplying the numbers in such a way that, look, starting from this place. Okay, so maybe, yeah, okay, I think sorry. Yeah, okay, this, then this and this, I'm multiplying. Okay, I'm multiplying these things. Clear? So let me call this 1, let me call this 2, and let me call this 3. Basically what is 1 is nothing but a33 into a21 into a12. 2 is nothing but product of these 3 elements on this line, and third element, this 3, is nothing but product of these elements on this line. Similarly, if I do this pattern, okay, so now you see we have 4, 5 and 6 of course. Okay, so you have 4, 5 and 6. So the determinant of this matrix is nothing but 4 plus 5 plus 6 minus 1 plus 2, sorry, 1 minus 2 minus 3 of course. Okay, means if you check 4 for example, okay, so what is 4? 4 is product of these elements on this line, a13, a21, a32, a13, a31, no, a21, a32, plus 5. 5 is nothing but product of these diagonal elements, a11, a22, a33, plus, then this is a12, a23, a31, then minus. Okay, so you put minus sign. So 1 is again a12, a21, a33, minus 5, sorry, 2 is this a13, a22, a31, minus this 3 is a11, a23, a32. Okay, so you can see if you check this value and if you check this value, they are same. Okay, this kind of calculation is generally time saving if many of these elements in this matrix are zeros actually. Okay, so let's say for example here I put 1 0, here I put 1 0, and here I put 1 0, then ultimately out of these 6 terms, 3 terms will straight away give me zeros and I can calculate the rest terms. Okay, so like this there are many techniques if you want to calculate a determinant. Okay, but within the gate domain, majority of the determinants are solved not because of the way what we solve them, but because of the properties of the determinants actually. Clear? So that's why it's very much important to look at the properties of determinants, and that's what we'll see now. Is this clear to all of you? Did you understand? So I'm telling you, within the gate type of gate kind of questions and gate PYQs and all the gate related questions, if you check, the majority of the questions or majority of the determinants are solved not because of knowing these kind of different ways to calculate a determinant, but rather because of the properties of the determinants is what that makes the calculations simple in gate examination. Okay, clear to all of you? Vivek, Shashwata, Vaishya, Danush, Harikrishnan, Abdul, everyone. So please type in the chat box. Is this clear? Sagnika? Yes or no? Every one of you. Yes? Okay. Now let's check properties of determinants. Okay, so let's go to some properties of determinants. These are very useful properties, of course. Properties of determinants. Okay, so let's check what are the different properties you can have actually for determinants. The first, okay, it's clear, right? Yeah. So the first property that you can understand is determinant of AB is equal to determinant of A into determinant of B, of course. Okay, then second, determinant of AB is equal to det A into det B, of course. And then if A is a n by n matrix, then for a scalar k, then for a scalar k, determinant of k times a n by n is equal to determinant of a n by n is equal to k power n times of determinant of a actually. Okay, so this power n comes up. That value is negative means we can shrink length. Yeah, of course. Okay, I'm telling change. The change can be either stretching or decreasing. Clear? So let's see, this is k power n into det a. Now let's write some important properties. The determinant of upper triangular, this property is very important, it saves a lot of time. Upper triangular, lower triangular or diagonal matrix is product of the principal diagonal elements. Product of the principal diagonal elements. Okay, so the product of principal diagonal elements. Like for example, you can see A, B, C, 0, D, E, 0, 0, F. If I have this kind of matrix, okay, then if I have this kind of matrix, ultimately the determinant is nothing but, since this matrix is clearly upper triangular because all the lower diagonal elements are zeros, this is equal to just ADF. That's all. Clear? So likewise, you can take any triangular matrix, of course, upper triangular or lower triangular or basically diagonal matrix, then the determinant of that particular matrix is equal to the product of all the principal diagonal elements actually. Clear? Now let's see one more thing. For the determinant of a matrix is equal to determinant of its transpose. Determinant of its transpose. This statement is very important and in fact very powerful as well. Okay, so determinant of its transpose. Clear? And 5, you can check the determinant of every odd order skew symmetric matrix is 0. This question was very important and it came many times in GATE examination. Okay, why this is, how you can show this is, odd order means you can see if A is n by n, then n is odd. Okay, so n is basically odd in this case. Okay, like for example, you take 3 by 3, 5 by 5, 7 by 7, 20, 23 by 20, 23. You can take any skew symmetric matrix of odd order. Definitely it has 0 determinant. I can show you easily. Look, if you have, for example, A transpose skew symmetric. Okay, so you know skew symmetric. So this tells you your A transpose is equal to minus A. Correct? A transpose is equal to minus A, and this is of size n by n. So if this is of size n by n, then ultimately this is also of size n by n. Okay, because it's a square matrix and you are just transforming it. Okay, I mean just transposing it. Now if you take determinant on both sides, this tells you determinant of A transpose is same as det A. Just one property about this we have seen, and det of minus 1 power A. Okay, so you can see minus 1 times A, and determinant of this, if this is of size n by n, this minus 1 is a scalar, so this results in minus 1 power n times of det A. Is this point clear to all of you till here? Yes or no? Because this minus 1 is something like a scalar multiplication to this matrix capital A, and if this is minus 1, if you want to take this minus 1 out of the determinant, since this is a n by n matrix, you will have minus 1 power n times. Correct? Like for example, you can see in this determinant, if I multiply every number with k, if I multiply every number with k, this is nothing but k times this matrix. Here in every number I would have got k, yes or no? K here, k here, k here. Similarly, k at all these places, and finally I would have got a k cube, of course. Okay, so that's why we have power n coming out. So now let's see in the here, if you have minus 1 whole power n det a, this determinant can be written as minus 1 whole power n times det a. So this implies if you take det a common, you have 1 minus of minus 1 whole power n is equal to 0, of course. Okay, so if you bring this term to the other side, we have 1 minus this minus 1 whole power n. Now if n is even, for example, then you cannot decide on this determinant. The reason is, if n is even, this minus 1 whole power n becomes 1, and this 1 minus 1 is 0. It doesn't matter whether det a is 0 or not, you cannot confirm in that situation. So you cannot say whether this det a is 0 or not. Okay, so this is 0. But if n is odd, if n is odd, minus 1 whole power n is equal to minus 1. This implies 1 minus minus 1 whole power n is equal to 2 actually. Okay, then this scalar is not 0, and this is product of two scalars because this is determinant of a, it has some value actually. Okay, so some value multiplied with 2 will actually give you 0. So this implies 2 times of det a has to be 0. This can happen only if det a is equal to 0, of course. Clear? So that's why this is actually 0 always. Clear? So this you can 100% say that is 0, only you can say if n is odd. If n is even though det a is 0 or non-zero, this equation is always fine. N can't be of order 1, at least 3 should be there. No, need not be. Okay, because you can say this matrix itself is also a skew symmetric matrix. Okay, that you can say. Fine. Is this clear to all of you? Because this point is a bit analytical point, and which is good to know about. Okay, so is this clear to all of you? Did you understand? If you take any skew symmetric matrix of odd order, definitely its determinant is a 0. What if 1 is the element? 1 didn't get you. Here if you have 1, that's not skew symmetric, correct? Because 1 cannot be equal to minus 1, that's it. Simple. Okay, now let's see if this is point number 5 for skew symmetric matrix, and that's why later stage you will see every skew symmetric matrix will have of odd order, of course, will have 0 as one of the eigenvalues. Okay, we'll see why it is there. So let's see here. 6. Okay, so number of term. Okay, fine. So we'll see that. Let me tell you one more point. So after this symmetric point, we went to orthogonal. Yeah, let's talk about orthogonal. The determinant of an orthogonal matrix is plus or minus 1. Is plus or minus 1. That's it. Okay, you can again show this like A into A transpose is equal to I. So if you take determinant on both sides, since two matrices are equal, their determinant should be same, det I. So this is product of two matrices, det A into det A transpose is equal to, identity matrix has determinant equal to 1, and since this det of A transpose is same as det A, we can write det A whole square is equal to 1. So det A is equal to plus or minus 1, of course. Okay, so plus or minus 1. Clear? So this matrix has got a plus or minus 1. That's it. Now similarly, if you go with involutory matrix or idempotent, all these things. So first let us go with involutory. The determinant of an involutory matrix is again plus or minus 1, of course. Okay, again you can show involutory is A square is equal to I. So this implies det of A square is equal to determinant of I. This can be written as det A whole square. This is also one important property, like det A square or det of A power n can be written as det A whole power n. Okay, you can write this here. Since det of A power n is equal to det A whole power n. This property is in fact very important. The reason is, many times what they give you, they'll give you a matrix A, okay, and they'll ask you determinant of A square. Then people will be busy in calculating A square, which is not needed actually, okay, because if you know det A, you can just raise it to the power 2, you'll get det of A square, okay. No need to calculate A square again independently. Clear? So that's why this property is a bit important. So det A whole square is equal to, this is 1. So det A is again plus or minus 1, of course. Clear? So that's what you have. Fine. So similarly, if you go for other stuff like the determinant of an idempotent matrix is 0 or 1 actually, okay. So it can be 0 or 1. Why I'm telling all these points is, let's say if I ask you a question, which of the following matrices do not have an inverse always? My options are orthogonal, then maybe let's say I'm asking MSQ, multi-select question. So which of the following matrices need not have an inverse all the time, okay, or always? Then first option if I give you orthogonal, second option if I give you involutory matrix, third option I'll give you idempotent, fourth I'll give you skew-symmetric matrix, okay. Then you know idempotent and skew-symmetric matrix, since they can have 0 determinant, they need not have the determinant, the inverse existing always, okay. So when these kind of questions are coming, you should be in a situation to say, okay. So let's see, this is 0 or 1. So idempotent, A square is equal to A, so det A square is equal to det A, of course. So det A whole square is equal to det A is equal to 0, of course. So this tells you det A is equal to 0 or det A is equal to 1, okay. So it's not mandatory that your idempotent matrix should always have an inverse, of course, okay. So this is something that we have. Then 9th point I would like to say, if sum of all the elements of a row or column is 0 for all the rows or columns, then the determinant of the matrix is 0. Then the determinant of the matrix is 0 actually, okay. Like for example, you can say A is equal to 7 minus 4 minus 3 minus 9 5 4 3 minus 7 4, okay. So let's say you have this matrix, then ultimately you can understand something. This sum of elements in this row is 0, sum of elements in this row is also 0, and sum of elements in this row is also 0. Then ultimately this matrix has a determinant which equal to 0. Clear to all of you? You need not actually calculate the determinant, just by looking and telling that since sum of each elements or sum of elements of each row is 0, then definitely it has 0. Similarly, let's say if sum of all elements of column is also 0, then also you can say the matrix has 0 determinant. Is this clear to all of you? Yes or no? So please type in the chat box. Is this clear to each and every one of you? Fine. Yes. Okay. So these are some properties which could be helpful, and one more property I would like to say, then we'll solve some questions. 10. If two rows or two columns of a determinant are interchanged, of a matrix, you can say of a matrix are interchanged, okay, of a matrix are interchanged, then the determinant changes its sign, without changing absolute value, without changing its absolute value, without changing its absolute value actually, okay. It's due to elementary transformations, right? Yeah, of course, good too, okay. So next 11th, I would like to say, if two rows or two columns of a matrix are identical or proportional to each other, okay, so are proportional to each other, then determinant is 0. Then determinant is 0 actually, okay. So you can have 0 determinant again in that case. So basically all these points you can see, especially point number 11, 10, 9, these are due to the O transformations, okay. So basically column transformations, basically by performing some number of finite operations on this matrix actually, okay. So all these are properties of the matrix. Property 10, if you interchange even times, then that will remain same. Is there any such rule? Yeah, of course. It's not like even time because yeah, 2 what you have told, but I'm just talking about 2 columns, okay. So if you're interchanging 2 columns, you can do it only once, okay. That's what. If you do even number of times, then again the matrix is same, okay. That's what. See, if you are doing even number of times, you have to apply the same property 2 times, that's it, or any even number of times, so it means the same thing, okay. So these are basically some properties of determinants which could help you out, okay, especially these properties regarding symmetric matrices, especially these things regarding the symmetric matrices, okay. This skew symmetric, then orthogonal, involutory, idempotent, then all these things it's equal. Many times I can to keep something, I can ask you a few things like, I'll give you a matrix and say it's orthogonal. For the given orthogonal matrix, I'll keep the element very complicated, okay. 2 by 7, minus 1 by 7, 4 by 7, this kind of stuff I'll keep. The determinant of the above matrix is, I'll give you options, okay. So +1, -2, 3, 4, something like that. And people who don't know the determinant of an orthogonal matrix is always plus or minus 1. What they do, they'll try to calculate the determinant, but actually you need not calculate the determinant because you all know the orthogonal matrix has a determinant of either +1 or -1. So ultimately, if only +1 is in the options, +1 should be the determinant of value of that matrix, okay. So these kind of understandings could be a good easy. So anyway, let's say we'll solve some questions now maybe. So come on, solve this question. It's a previous year GATE question, but of course a simple question. Okay, previously you have answered Sagnika, Gautami, Ashwini, Vasishta, Kids Gaming, all fine. So anyway, let's get back to the polls then. So let us solve this question. Fine. So this is the matrix. The determinant of A transpose into A inverse is dash. So I'm giving you some 60 seconds to solve this. Start. Solve this. There is a matrix A which is a 2 by 2. They are asking determinant of A transpose into A inverse of that particular matrix. Type, okay, so work it out and then type the answer. You have some 30 seconds more roughly. quick, fast, it's getting done. Okay. See, only 2 people are able to answer. Vasistha told A, secant square x, Sagnika C. Okay. So let's see. The correct answer is of course C. Joel, Abdul, yeah, of course, only 2 of you, and I think Vasistha, Sagnika by this time you have finished. See, I have given you 60 seconds to solve this question. You might have understood something. The job would have been a bit easy. Firstly, whoever is telling secant square x, I'm not asking the determinant of A. If I ask determinant of A, yeah, 1 plus tan square x is secant square x, but I'm asking determinant of A transpose into A inverse, correct? Okay, Samiksha is feeling it's B. Fine. So let's see. In fact, what are the matrix I give you, as long as its determinant is not 0, because this inverse should exist. Since they are asking A inverse, that matrix has determinant non-zero. Okay. So let's see here. I want, forget about the matrix for some time. I want determinant of A transpose into A inverse. Correct? A transpose into A inverse. This I can write as det of A transpose into det of A inverse. Correct? So det of A inverse is, det of A transpose is nothing but det A. Det of A inverse is nothing but det A whole power minus 1, because I told you since det of A power n is equal to det A whole power n, of course. Okay, I have told you this. So this is det A whole power minus 1. So ultimately these two cancel up and the answer is 1. That's it. Clear? Now to do this I have given you 60 seconds. But people are busy in calculating A transpose and multiplying A inverse and doing a lot of things. Yes? Yes or no? Correct now? How many of you tried to calculate A transpose into A inverse? Please tell me honestly. How many of you have tried calculating A transpose into A inverse? I know definitely few people might have tried calculating A transpose into A inverse. How many of you tried it? Okay, fine. Yeah, I know many of you might have tried this, but anyway, look here. In this case, det of A transpose into A inverse is equal to 1, and you can ask me, how do you know that this A inverse always exists for this matrix? Because if you calculate det A, this is equal to 1 plus tan square x, and this is always greater than or equal to 1. Correct? Yes or no? Because tan x is like 0. The least value that tan x can take is 0, of course, and this value is either 0, either 1 or something more than 1. Okay, so this cannot be 0. Clear? So that's why we know that A inverse exists for this matrix. Okay, in fact, any non-singular matrix that I have given you, this determinant is always equal to 1. C is the correct answer. Okay, so that's how you can understand the things. Clear? And guys, I want to give you 2 more points about determinants actually. Number of terms in the determinant. Number of terms in the determinant of a n by n matrix. And obviously you can calculate determinants only for the square matrices. So number of terms in the determinant of an n by n matrix, is, any idea? How many terms does an n by n matrix consist of? Any idea to anyone of you? No? Yes? How many terms does an n by n matrix consist of? No? Think. Try to think a bit. Let's say for example you have 2 by 2 matrix. Okay, let's say you have 2 by 2 matrix A, B, C, D. So this consists of 2 terms clearly, AD minus BC. So 2 terms you have to simplify and get the answer. Then how many terms you have in a 3 by 3? Let's say if you calculate 3 by 3 matrix, let's say for example you have A, B, C, def, GHI, you get AEI minus AFH minus BDI plus BGF plus CDH minus CEG is what you get. Can you tell me total how many terms you have? Sir, there is a problem. I cannot participate in full form unity. I think it should be active. Okay, no issues. It comes up. Okay, Shashwata, just try to refresh the YouTube tab or something. You can you can give it a try. Okay, so you can see how many terms do we have? 6. Okay, so we have 6 terms. Similarly, if you calculate a 4 by 4, can anyone tell me how many you have? If you calculate a 4 by 4 matrix, can you tell me how many do you have approximately using this algebra? 2, 6. Anything that you can connect? If I keep doing this business for 4 by 4, then how many terms do you expect? 8, 12. It's actually 24. Okay, so this is n factorial. You'll have these many terms in a matrix. In a determinant actually. Okay, so this is what you have. So total 6. This is basically 2 factorial. This is of course 3 factorial. And if you expand a 4 by 4, you'll see 24 factorial is what you'll get. Okay, sorry, 4 factorial, which is 24, of course. Okay, so that's what you have. So that's n factorial basically. So if you keep expanding a n by n determinant, you will end up with total n factorial terms in that determinant. Fine. Yes or no? Clear? No, it's actually 24 terms. You can check. Okay. I can easily show you it's 24 terms. If you have A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, then it's clear that you have A into determinant of F, G, H, J, K, L, N, O, P minus B into E, G, H, I, K, L, and M, O, P, of course. Okay, plus C into E, F, H, I, J, L, of course, and we got M and P minus D into E, F, G, I, J, K, M, N, O. This is what you will get. Correct? Now you can understand one thing. In each term you have 6 terms. Correct? Like, because every 3 by 3 determinant, if you expand, you will get 6 terms actually. Okay, so here you have 6 terms, here you have 6, 6 and 6. So total 4, 6, you have 24 terms. Okay, yeah, Abdul, correct. Basically 4 into 6 terms of 3 by 3. Correct, exactly. Okay, so you have total 24 terms. Got it? Which is basically 4 factorial. Okay, is this clear to all of you? So this term is also a bit important in general, and I hope all of you know a shortcut for calculating 2 by 2 inverse. If you have A, B, C, D, then this is something like A inverse is equal to 1 by AD minus BC, such that this matrix don't have this AD minus BC equal to 0. Okay, then you have, just you can flip these two, D, A you can flip, then you can put a minus signs for the other elements. That's it. Okay, so that's a simple 2 by 2 way to calculate, and I think you guys may have done it many times in your life. Just if you have a 2 by 2, inverting is very simple. Of course the funda is same, calculating minus, doing cofactors, then transposing, all this business is same, but that's the way, that's the matrix that you will get finally. Okay, 1 by delta A into adjoint A, this will be a adjoint A. Clear? Then let's see, let's solve one more question to be frank. So consider the matrix J6 is equal to this, which is obtained by reversing the order of the columns of the identity matrix. Like for example, you see, if you swap this, then this is the first column in an identity matrix, this is the second column, third column, fourth column, fifth column, and so on. Then P is equal to I6 plus A into J6, where A is non-negative real number. Where A is non-negative real number, the value of A for which determinant of P is 0. Okay, so P is basically I6. I6 is the identity matrix of order 6 by 6. J6 is this matrix. So P is basically solution. J is or P is equal to I6 plus A into J6. So P is equal to identity matrix of order 6 by 6. So 1 0 0 0 0 1 0 0. This is what you have as I6. Okay, then if this is I6, then you are multiplying A times of J6. So if you multiply A to this matrix and if you add, you will finally end up with this element will be A. Similarly, this element will be A, and similarly this guy here will be A, then this will be A, this would be A of course, and again this also would be A here. Clear? This is what you will get P. I6 plus A times of J6 is what you will get. So for me, more than 2 by 2 for finding A inverse, tell me shortcuts, sir. See, basically you have to see in exams na, when they give options to calculate A inverse, please don't keep calculating A inverse. I have one question which shows you. Okay, so whenever you have A, they give you A, and if they are asking you A inverse and let's say 4 options are given, you have to tick one. Ultimately, you know, if you multiply these two, you'll get identity matrix, correct? So multiply this O with the first columns of all these things. Okay, and many times it happens only one of them gives 1, the other things give some other values actually. Okay, if this is also matching, multiply this first O with second column, you should get zeros. So like that you can follow the elimination procedure in order to get the inverse very quickly. Okay, fine. Yeah, now let's see. If this is the matrix and you want to calculate the value of A for which this matrix will have 0 determinant. Okay, so you can see A is non-negative real number, the value of A for which P is equal to 0. Can anyone tell me anything by doing something? Look, I'll tell you actually. First of all, by visualization, if you just see by visualization, by visualization, just if you look at this matrix, you can observe something. For A is equal to 1, first row and last row will be same, second row and fifth row will be same, third row and fourth row will be same. So this implies that P is equal to 0. That's it, correct? It's not identity matrix. Okay, it is some different matrix. You have one A is not equal to 0. Okay, they have given non-negative clearly. Okay, just by looking you can say that this, when you put A equal to 1, first row and last row they become identical, second and fifth become identical, third and fourth become identical actually, right? Yes or no? And A is non-negative, it is 1 actually in this case. Clear? I've told you, right? If 2 rows or 2 columns of a matrix are equal or proportional, then definitely determinant of the matrix is 0. So when you put A equal to 1, then definitely you can see this actually matches. Okay, or if you don't know this, then you can do one more point, or let us apply some transformations and let us make these elements zeros, for example. Okay, if you make these elements zeros, the advantage that you have is all these diagonal, lower diagonal elements are zeros, then you can calculate determinant just by multiplying the principal diagonal elements. If I apply R6 changes to R6 minus A times R1, R5 changes to R5 minus A times R2, R4 changes to R4 minus A times R3, then the matrix gets converted to the form or P, that P is equal to, first 3 rows you are not changing anything, so 1 1 2 3 4 zeros, and this is A of course, then 0 1 0 0 A 0, then after 0 0 1, then A 0 0 actually. Now coming to the fourth row is fourth minus A times of third. Okay, sorry, code for max discount on batch, I think First of all, there is no codes in this case, okay? To be honest, you can there is nothing like code or anything that you have to use for discount, but whatever the discounts are available, they'll just openly tell it on the YouTube platform of 𝐂𝐸 𝐂𝐸 English, 𝐂𝐸 respective branches of mechanical, EC and all. So you can just follow the procedure to buy, that's it, okay? There's no code or nothing. Clear? Now let's see fourth. Now 4 changes to R4 minus A times 3. So 0 minus A times of this 0, 0 minus A times of this 0, A minus A times of 1 0, 1 minus A times of A, you have 1 minus A square. Similarly, this is 0 and this is also 0. Similarly, if you do for R5 and R6, you will get 0 0 1 minus A square 0 0 0 0 0 0 1 minus A square. This is what you have, okay? Now clearly this matrix has a upper triangular matrix, okay? Because you can see all these lower diagonal elements are zeros now, because this is the diagonal. I'll just show you maybe. So this guy is the diagonal and all the elements below this diagonal are zeros. So determinant of this matrix, now this got converted to upper triangular because all lower diagonal elements are zeros. So if these are zeros, det P is equal to 1 minus A square whole cube. That's it. So this has to be 0. So this implies A square minus 1 or maybe 1 minus A square has to be 0. So this tells you A equal to plus 1 comma minus 1, but you cannot take minus 1 because in the question they have mentioned A is non-negative, okay? So this is non-negative, so ultimately you cannot take minus 1. So A is equal to plus 1 is what you have. That's what we have observed even by visualization. For A equal to 1, these things happen and that P is 0. So this value is 1. Clear? That's what. Fine. Oh, thank you, Abhigyan. Is this clear to all of you? Yes or no? This value is 1 for which this particular combination P equal to I6 plus A times of this matrix, which gives you this matrix, has a 0 determinant. So can you please tell CK to remember multiple subjects together, please? Revision, pure revision is what you have to do, okay? We'll see how to revise and all. Maybe in tomorrow's class I'll spend some time and we'll explain, okay? Now I'll give you some homework, so please try out. I have solved some questions today. So this question is for homework today. Homework, and we have solved this question. So the next question, this question is also for homework. Yeah, this question is also a good question. You do it for homework, okay? So these questions and this also, yeah, you give a thought about it and think, okay? So 4 questions, we have homeworks. Clear? So general doubt, there is any full length course planning for EE electrical machines and power systems like this? Yeah, the plan is on the way, okay? So you mistook it. Best of luck. Okay, good. Abhigyan, fine. Yeah, it's okay. You learn from any place, it doesn't matter, but the ultimate point is you should get some knowledge. That's all. When does the principal cofactors A11 equal to A22 equal to A33 become equal? Depends on the determinant. That's it. Okay, purely depends on the matrix. Like let's say if the matrix is containing all same elements, okay, then also it can happen. Okay, so we have things like that. Okay, 7. Okay, so these questions you please try it for homework. Okay, so anyway, in couple of minutes you can see basically what we have done today is we talked of things like idempotent, involutory, nilpotent matrices. Okay, so we have talked about these things, nilpotent matrices, and then we came across the definition of a determinant and properties of determinants. Properties of determinants. Clear? So these are the things that we have seen, of course, and So yeah, that's it basically. So we'll again meet at tomorrow 7 p.m. because tomorrow's lecture is really like we'll talk about a bit of vector spaces and we'll talk about the most important concept, the rank and system of equations. Clear? So we'll be teaching fluids on thermo in Paracam D batch. I teach in English batches. Okay, I teach both fluids and thermo, both I am teaching in English batches. Clear? Does it mean any specific case? We'll see. Okay, so let's go to eigenvalues, then we can observe. Okay, we'll talk a bit detail about this cofactors there in eigenvalues. Clear? So we'll again meet tomorrow at 7 p.m. So tomorrow we'll talk about vector space, and also if time permits I'll look at partition matrices. Okay, so we'll go into all these things, and that's all. Thank you. Okay. Law of reversal, but I think it's not in the syllabus of anything, but it's okay. If you need something, you can just upload in, you can just if you have some queries, you can, regarding the law of reversals, you can just mention it in this Telegram groups. Okay, so once again I'm displaying, this is the Telegram channel for the Get Wallah English. So any update on this channel turns up here, so please I suggest you to join this, okay, so that you don't miss out any sessions. And similarly here you have this is my personal group, personal instance with my PW students, of course, and we all together manage this group. Okay, so if you want to have be in touch with me, you can just join this. Okay, yeah, so that's all for today. Then we'll meet tomorrow again at 7 p.m. and we'll look at a few things else. Okay, any questions by the way? Thank you all, thank you for so much of love. Then thank you, that's it. Okay, yeah, so good night, signing off.